right, welcome to another presentation for differential equations. In our third module here, we're going to look at a couple of specific types of nonlinear differential equations. So you remember in the last video, we were focused on first order linear differential equations. We distinguished between linear and nonlinear and learned how to solve all first order linear differential equations with our methodologies. We don't have a methodology to solve all first order nonlinear differential equations, but instead we have some techniques that'll work in some specific cases. And one of the most common techniques you'll see for these is the separable differential equations. Technically, they don't have to be nonlinear to be separable, but we will see that some nonlinear first order ODEs are separable, and this gives us a way to solve them. So in some sense, we are just separating the variables, putting the dependent variable and its derivatives on one side and the independent variable on the other side. But that's actually not an exact description of this because you really need the y and y prime to be written in the formula you see here on the left. It has to be y prime times a function of y. And so, for instance, if I had a differential equation that was y prime plus y equals x squared, right? That's actually not separated according to this separable format because h of y isn't multiplied, right? It's being added. So we do need to separate the variables, but we also need it to be y prime times a function of y. So keep that in mind. Here we see an example of a separable first order ordinary differential equation. Also notice that it is nonlinear because of the y squared. And we can separate this one by multiplying both sides by that denominator expression, 1 plus y squared. If we do that, then we get the 1 plus y squared times y prime on the left, and then the x on the right. And in that case, h of y is 1 plus y squared and is multiplied by y prime, and g of x is just x. So that's an example of a separable first order nonlinear differential equation and the separation process. All right, here's another differential equation. This one is also nonlinear because of the y squared. It's also first order. And it is also, I think it's separable. Yeah, I think it's also separable. That's what I have drawn up. And so sometimes it's not as obvious how to do the separation. So if you think about this format of this formula here, we want y prime on one side. Sometimes it's helpful to get everything else on the other side first. And so, for instance, here we might subtract the other two terms, leaving y prime on the left where we'll want it. And then another common trick that you'll see to help with this is factoring. Factoring can kind of separate the terms. And we look here, we have a common factor of negative x on the right side. Factoring the negative x allows us to separate the x and y variables. At that point, we can now divide both sides by y squared plus 5y. And in this case, g of x is negative x, and h of y is really 1 over y squared plus 5y. So it can be y prime divided by a function of y, or multiplied because multiplication and division are related through that reciprocal relationship. It just can't be y prime plus a function of y or y prime minus a function of y. All right. So this is another example of a separable first order differential equation. We have an example here for you to try out. Sine of x times sine of y plus cosine of y times y prime equals 0. So this is indeed a first order nonlinear differential equation. And you want to see if you can separate it. So maybe it's separable in the form of A or B, or maybe it's not separable at all. Give it a try. Go ahead and try to write that out and separate it. All right, pause if you need more time. Um, but I think we'd want to subtract the sine x, sine y to the other side. And then we'd want to divide both sides by sine of y. And then cosine y over sine y is cotangent y. And we can see it matches up with answer choice B, so it is indeed separable there. So the h of y function is cotangent y, and then the f of x function is negative sine of x. So correct answer is B. All right, here's another example. Dy over dx equals x plus y. Pause if you need more time. So if we try to separate the variables, there's not really a way to multiply or divide by a function of y without taking x with you. And if you subtract the y from both sides, we do indeed get answer choice A. So A is an equivalent representation of the differential equation, but also it's not in the required format. Remember, the required format is y prime h times h of y equals x. And so that's not the derivative times a function of y, it's the derivative minus a function of y. So A and C are technically both correct. We can separate the variables in the looser sense, but this is actually not a separable differential equation. We wouldn't be able to proceed with the rest of the procedure. So correct answer is C, not separable. Got one more for you. Okay, that's a pretty tough one because of the rational expression there. But you can indeed separate the variables. So multiply by the denominator. And then you'd want to distribute. And then you'd want to separate x and y terms. So subtract that. And subtract that. And then you can factor the x. You can also factor that y. And then you can divide. And it will turn into that one. However, so you have y and its derivative on one side and you have x on the other side. But again, remember our formula was y prime times h of y equals g of x. And so having y prime appear multiple times there in a way where you can't put it in that format This is more of y times h of y prime than y prime times h of y. So B is an equivalent differential equation, but this is not separable according to our formula. So we see it's more than just separating the variables, though that is the strategy to see if it's separable. Go ahead and separate the variables and then see if it fits that formula. Now, when we solve these separable differential equations, we will often get what are known as implicit solutions, where we can't solve for y explicitly as a function of x. Going back to module 1, that means that we'll look at those graphs as integral curves rather than full-on solution curves. This is an example of a first-order nonlinear differential equation where we can model it as separable, and we'd multiply both sides by that denominator, 5y to the fourth plus 1, and we have separated it. And then the next step in the process, which is pretty short and simple, is to integrate both sides. And when you integrate the left side, you get y to the fifth plus y. And so you have this implicit solution relating x and y. Notice it's a general solution. And it's not possible to solve for y explicitly as a function of x, at least in any usable form or with any basic algebra techniques. So this kind of thing will happen, and what we will do is we'll just work with the implicit solution. A lot of graphing tools will allow us to graph these, and we can use implicit differentiation to find derivatives of these things. And so we may just be forced to work with an implicit solution rather than an explicit one. Another type of differential equation that's nonlinear are the so-called Bernoulli equations. These are named after Jacob Bernoulli, shown here in this photo, though there are a whole family of these Bernoullis, and several of them were famous mathematicians. And the Bernoulli differential equation has this format. It is a first-order nonlinear differential equation. Now, this looks a lot like our general form of our first-order linear differential equations. And what sets it apart is this additional y to the r factor here on the right side. So rather than the forcing function just being a function of x, you have y to some power. And that r is anything other than 0 or 1. If it's 1, you could combine it and it's linear or homogeneous. And if it's 0, then it's y to the 0 is 1 and it becomes linear non-homogeneous. But it can be negative or a non-integer value. So here's an example of a specific Bernoulli differential equation. In this case, p of x is -1, f of x is x, and r is 2. So it is good to identify p, f, and r when you are working through this. It'll help with following the methodology. And in the methodology, we'll see that we can solve the homogeneous form of this, which will just replace the right side with 0 and will be the same as kind of a linear homogeneous. And then using that homogeneous solution, we can actually make it a separable differential equation. So we'll learn separable first, and then we'll be able to make this one separable. As it is in general, it's not separable for every value of r. For some values of r, it will be, but it's not. Oh, and I think I misspoke here. So I didn't see that these were switched. So to put it in the standard form, we'd actually need to multiply by -1. So p of x is still -1. Okay, so I was right about that, but I was kind of identifying in a weird way. But f of x is -x, and then r is equal to 2. All right, so I have an example for you to try. So here's an example of a Bernoulli differential equation. Put it in standard form and then identify P of X, F of X, and R. I'll give you a second to do that. All right, pause if you need more time. To put it in the standard form, we'd want to divide by x squared. And then it might help to write that square root of y as y to the 1/2. Now that y to the 1/2 is what makes this nonlinear. And then you can see that P of X is 2 over x squared. And F of X is 2 over x squared times e to the x. And then R is the 1/2. So now should be able to handle the two methodologies, one for separable and one for Bernoulli differential equations, which are both going to work for some nonlinear first order differential equations. Before we wrap up, I just want to mention that this presentation doesn't contain images and text from the elementary differential equations of boundary value problems by William Trench, which is Creative Commons CC by NCSA, and is available at the Digital Commons URL there. So I got it from LibreText. So thank you, Trench. All right, I'll see you all in the methodologies and then in the next presentation.